Okay, let's get started. I hope you can hear me. Okay, so last time we looked at message authentication codes, and the idea was that if you are sending a message, you want to prevent it from being tampered in transit. And for message authentication codes, the sender and the receiver had to have a shared secret key, right? So you cannot really use message authentication codes unless you're talking with somebody who you already know, who you have met and have generated a key and so on. So for example, again, let's say you're opening some kind of website, let's say google.com or something like that. You cannot really use message authentication codes because you don't have a private shared key with Google, right? So you need something different, and this is where digital signatures come in. So very roughly, the difference between digital signatures and MACs is somewhat similar to the difference between public key encryption and secret key encryption. In digital signatures, only the person holding the secret key can sign, but then everybody who has the public key can verify your signature. Okay, so let's try to define what digital signatures are. And as you know, digital signatures are basically used all over the internet. They are used in the HTTPS protocol and so on. So it's really, it's one of the backbones of of security over the internet. Okay, and the idea here is that everybody can verify, even though the only person who can sign is the one holding the secret key. So again, any digital signature scheme must have three PPT algorithms. The first one being the key generation algorithm, as always, and this algorithm outputs a secret key and a public key. Okay, you can publish your public key in a newspaper or on some website or something like that. And then let's say you want to sign a message M. So then you would use your secret key SK and the message M, and this algorithm would output a digital signature, which we will denote by sigma. And then finally, similar to MAX, we will have an algorithm which is called verify algorithm. So this algorithm does not take the secret key. Instead, it will take the public key as input, it will take the message, and it will take the signature, and it will output 0 or 1, accept or reject. And then there are two properties which this system has to satisfy. The first property is correctness. And correctness just says that you generated the key pair correctly, you signed correctly, then the verification algorithm will always accept. So correctness says that for every message M, probability that the verify algorithm, which takes as input the public key, the message, and the signature sigma, we are looking at the probability that this outputs 1 or this accepts, conditioned on generating the public key and the secret key correctly from the key generation algorithm. And then finally, sigma is sign of SK comma M. This probability should just be 1. Right? So this is what happens in the honest execution of the system. And what do we want from security? And by the way, the security for digital signatures is also known as unforgeability, just like MAX. So again, it's almost identical to Max. So we will consider a challenger and a PPT adversary, right? The challenger generates the secret key and the public key and gives the public key to the adversary. Adversary can look at the public key, can decide a bunch of messages, and can ask for signatures on all these messages. And then the goal of the adversary is to output a signature on a new message, which passes the verification test. If the adversary is able to do that, we say that adversary has won, and we want the probability of adversary winning to be negligible. Okay, so again, we have a PPT adversary A, we have a challenger C, and let's have various stages. Stage 1 is the keygen or the start stage. So here the challenger generates SK and PK from key generation. Challenger keeps SK to itself and sends PK to the adversary A. Okay, so second step is learning, where for all I from 1 to Qn, where Q is some polynomial, A sends some message M of I, and C responds with sigma I, which is the signature on this message with the secret key. Okay, and then finally we have the forgery. A has to output some message and signature. A wins if for all I, M is not equal to MI, so it's a new message, and yet at the same time the signature is accepted. The signature is valid, which means that verify of PK, M, and sigma is 1. Okay, and what we want is probability of A winning must be negligible in the security parameter. Okay. So hopefully the definition makes sense, very similar to the previous definitions. And there's a weaker notion which we will consider and which we will construct first. And this is known as one-time signatures. And here the adversary only gets to make a single query. So here, which is the same, but the bound on the number of queries is 1. So in other words, A sends M1, gets sigma 1. Then immediately after that, A doesn't get the opportunity to make any more queries. A has to output M and sigma right away. Okay, So one-time signatures, it's a weaker primitive because we only require security against a single query. Yeah, one-time signatures are somewhat easier to construct compared to general multi-time signatures. So if you have a one-time signature scheme, you only want to use it to sign a single message. If you sign even 2 messages, then maybe the security is just completely gone. Okay, and by the way, the digital signatures were introduced by Diffie and Hellman in their seminal paper in 1976. The paper is called New Directions in Cryptography. That's the paper which really introduced a lot of these things, including public key encryption, key exchange, and digital signatures. And there's an interesting story behind this. Diffie and Hellman, they imagined the notion of digital signatures. They imagined that that's something which can be very useful, but they were stuck on building digital signatures for a long time. And then they were having lunch with this researcher. His name is Leslie Lamport. He doesn't even work in cryptography. He works in distributed computing. And they mentioned the problem of digital signatures. They said, oh, it's very interesting, but seems like a very difficult problem to solve. And within a few minutes, Lamport had a solution for digital signatures, and that became the first ever digital signature scheme. And the solution appears in the paper of Diffie and Hellman, but in the acknowledgement section, they do credit Lamport for suggesting this solution. And Diffie and Hellman, of course, they got the Turing Award later on for their paper. Leslie Lamport also got the Turing Award, but for completely different things, for a body of research in distributed computing. Okay, so let's look at the Lamport signature scheme. Lamport one-time signature scheme. And the interesting thing here is that, as I mentioned before, we don't know how to construct public key encryption from secret key encryption or one-way functions. Typically, we would think of digital signatures as something in the class of public key encryption. There's a public key, there's a secret key. But on the other hand, we do know how to construct digital signatures from any one-way function. That's something which is pretty interesting. Okay, so we will just use a one-way function. And we will use this one-way function in a generic way to build one-time signatures from this. And let's say the message length is so length of the message, let's say, is small n. Let's say a security parameter. We can talk about smaller and larger messages as well later on. So how does key generation work? So in key generation, SK is just a bunch of 2n random strings, or n pair of random strings. So x01, x02 up to x0n, and x11, x12 up to x1n. And they're all uniform. Uniform from the domain of one-way functions. So this is your secret key, long secret key. What is your public key? Public key is just the one-way function f applied on each of these strings. So y10, y02, y0n, and y11, y12 up to y1n. Where ybi is equal to f of xbi. Okay, so just the one-way function applied to each of these strings, and just a sanity check, it's clear that you cannot compute the secret key from the public key because you need to invert the one-way function if you want to do that. And how do you sign the message? So the signature is, we take these n pair of uniform strings and we choose one string from each pair depending upon what that bit of the message is. So in particular, if the first bit of the message is 0, we will pick this. If the second bit is 1, we will pick this, and so on. And we will just concatenate all these things. So sigma is basically x1 m1, where m1 is the first bit, concatenation x2 m2, where m2 is the second bit, xn mn, and here mi is the ith bit of m. Okay. How does the verification process work? So sorry, this sign has to take secret key. The verification process only takes the public key, takes the message, takes the signature. And how do you verify? Well, you take the n components of the signature, you apply the one-way function, and then you match it with the value inside the public key. So you want to check if for all I, yi is equal to yi of mi is equal to f of xi of mi. If so, accept. Else you reject. Okay, so the high level idea here is that you have an n bit message, and that message basically selects like a bunch of these images of the one-way function, and the signature has to contain the corresponding pre-images. Okay, is the scheme clear? Should we go to the security proof? Okay, and the security proof is actually very simple, because if you want to change the message, let's say you want to change the first bit of the message, then you have to invert the one-way function. Then you have to output a pre-image which was not part of the original signature. What role does the length of the strings play in our scheme? Does it affect security? Well, Xi's are from the domain of the one-way function. Okay, and as long as it's a one-way function, it's fine. You work with whatever domain it specifies. Okay, so one-way function from the domain to the range, and for all I, this must be from the domain, or rather, it's sampled uniformly from the domain. Any other questions? So correctness is straightforward. Let's skip correctness. Let's go to the proof of security. Okay. So remember that it's only a one-time signature scheme, so the adversary gets to see a single signature on a single message. So we will prove it by contradiction. Suppose you are given a PPT adversary A. And what does A do? A queries with some message. Let's call this message M1. A receives as response the signature sigma 1. And then finally, A will output M and sigma as the forgery, where M is not equal to M1. Right? So this is the security game. So if M is not equal to M1, then there must exist a bit where they differ. So let me call this bit to be, actually I want to use the subscript notation. Let's call this M prime. Okay. And suppose the ith bit of M is different from the ith bit of M prime. Okay. They have to differ in one of the bits. Let's say that that bit is I, that position is I. Okay. Then let's look at the intuition first before going into the formal proof. Then what does A gets? A gets X of Mi. And by the way, for simplicity, let's even say that Mi was 0 and Mi prime was 1. You can do the other case in the same way. Then A gets X0 of I as part of the signature is called sigma prime. As part of sigma prime. Now the interesting part is that A has to output X I of 1 as part of sigma, right? And can you compute Xi of 1 from Xi of 0? Well, no, they are all independent, random, uniform strings. There's no relation between the different xi's. So essentially, A has to output this xi of 1 as part of sigma. And A is just given f of this number, xi of 1, which is yi1. Okay. So essentially, A has to invert the one-way function here. So this is just the intuition. This is not the complete proof because we basically have to construct B. B is an algorithm which would invert the one-way function. So we have to be a little bit careful here. Okay, so let's put this in the intuition. Now B takes y as input. Okay. Now what does B do? B has to choose the public key first. So the idea is that B would act as the challenger, B would invoke A, B would get the forgery, and based on that, B would hopefully invert Y. Right? So now the question is, what does B do with Y? So this proof is a little bit different from the previous proofs that we have looked at so far. Because B only gets one Y as input and has to sort of produce the public key, which has 2 n images of the one-way function. Any ideas? Okay, so here the idea would be that you put Y in a random location. So you have 2 n possibilities where to place Y in the public key. You just pick one of them at random, and that will be Y. The other ones B will choose on his own. And the idea is that with probability 1 by 2n, that is the Y which A will end up inverting. Okay, and if the original probability was noticeable, even if you divide it by 2n, the result is still noticeable. So that's basically the idea here, and this idea is used in a lot of different places, in a lot of different security proofs in cryptography. Okay.
But how can we control which bit A differs on? Maybe A always differs on the first bit, for example.
Yeah, so the point is that if you choose your location at random, then the probability that it will end up becoming the same as the location which A chooses would be like 1 by 2n.
Okay, that makes sense.
And in fact, you know, as we will see, there's also another problem. So B takes Y as input, chooses, let's say, let me call it I tilde and B tilde at random. And then you set Y equals Y of B tilde and I tilde. Okay. Now, or rather the other way around. So this is where we planted the challenge. For others, B chooses X BI on his own. Okay. And then B sends the public key PK, which is equal to all the on his own and compute YBI equals f of x bi. Okay. So observe that B knows the preimage of 2n minus 1 of these strings, but there's one string which B doesn't know the preimage to, and that's y, right? And B is hoping to get the preimage of this string. Okay, and then you send the public key so constructed to the adversary A. Okay, now we are not done. The adversary is just not going to reply with a forgery. Adversary is going to query. So A queries with the message M prime, and now B has to respond with a signature on M prime. B might not always be able to do that. The reason for that is that B does not have the complete secret key. One of the preimages is missing. Okay. So if sigma prime needs the preimage of y b tilde I tilde, which is also equal to y, A just B aborts. B is not capable of computing a signature here. Right? So by the way, this would happen with probability half. Otherwise, else B can compute the signatures sigma prime. And then finally, at the end, A responds with some signature M comma sigma. Okay. If sigma has preimage of y beta tilde I tilde, B is done. Else again B fails. Okay. And what is this probability? The probability that B aborts here, this is like half. And what is the probability that sigma has the preimage of this y? So this is just 1 by n. Okay, so this probability is the same as the probability that this is the same as probability that M and M prime differ in precisely I tilde bit. Okay, and since they differ in at least 1 bit, maybe more, This probability is at least 1 by n. Okay, so it seems like with probability 1 by 2n, B is successful if A is successful. This means that if A was successful with noticeable probability, B would also be successful with noticeable probability. So this is basically the whole proof. Okay, so let's move on to to multi-time signature, or even before that, let's move on to the length of the message and how we can deal with that. So by the way, the limitations of this signature scheme are actually very similar to one-time pad, right? Here, the key grows with the length of the message, and you can only sign a single message. Right, the size of the secret key depends on n, where n is the number of bits in the message. Similarly, the size of the public key would grow. So just imagine you wanted to sign a very long, let's say 1 gigabyte long file. This system is going to be really inefficient.
Also, wait, just as a detail, wouldn't you need n not to be the number of bits in the message? Like, it feels like you need some higher granularity, whereas if like each x10 and x11 was a bit, then the like set of functions from x10 to x
Yeah, so
y to y0.
So these
be very
strings cannot be bits for sure.
Okay, so then like n
they are from
like,
the domain of the one-way function, and yeah, so that's why it's not even 2n bits. It's really 2n strings.
Okay.
So
n would be something you would use, like n is maybe like the square root of the bits, or what would you do in practice?
So n is really the security parameter. You can think of,
Okay.
I mean, you can think of n as something like 100, right? So here, I used the length of the message to be n as well as the security parameter to be n. There's no reason that these two should be the same. I just did it for convenience. So here, the length of the secret key, I can try to compute. Length of the secret key is equal to length of the message times length of each xbi, and the length of each string in the domain is something like this is something like n bits.
Okay, thank you.
So this is at least as long as the size of the message, but in fact much longer than that. So definitely a good starting point, but not the ideal solution. We can have a one-way function from 1-bit domain. No, so yeah, keep in mind that you cannot have one-way functions with 1-bit domain, because that's very easy to invert. I can just try both inputs, and one of them is going to match the output. So the only reason we were able to construct one-way functions is because the domain was very large and you cannot exhaustively try all possible inputs. Okay, so there are sort of two limitations which we will try to overcome. One is, what about the length of the message? And second is, what about signing multiple messages? Turns out that unlike one-time pad, here you can keep going further and you can modify the scheme to overcome both of these limitations. So first, let's look at signing a longer message. This is not that hard. In fact, I already talked about it at some point in one of the previous lectures. Any idea on how we can do this?
Hash and sign.
Yeah, you can just hash the message first. You can use a collision resistant hash function, and you can just sign the output. So we will assume a collision resistant hash function. Let's say the function takes as input something which is very long. Okay, and there are hash functions like that. They can take an input of arbitrary length and just produce a fixed length output. So let's say the output is just n bits, where the hash function is chosen from a collision resistant hash function family. And this hash function must be public. It's part of the public key. Okay, and then what you can do is your you output you just sign with the public key as before, hash of the message rather than the actual message. Okay, and then how do you verify? And let's say this is sigma. The verification will have two parts. First, you want to ensure that the verification algorithm, I keep writing PK, should be SK in the signing. So first you ensure that the correct hash is signed, and then you want to ensure that H of M is correct, given M. Okay, and why is this good? Right? Why can't we just sign the hash of the message? Is this even secure? Is this a valid signature scheme? So again, we are doing it in the context of one-time signatures, but the same argument applies even for multi-time signatures. So let's try to prove it by contradiction. By the way, is the scheme clear? This is famously known as the hash and sign paradigm, which is used everywhere on the internet. So let's see why this hash and sign is good, is secure. So, so again, we'll prove it by contradiction. Say adversary sees the signature M1 sigma 1 and outputs another signature M and sigma. And now we can consider two different cases. Case one is H of M1 equals H of M. So here A found a collision in H, which contradicts the assumption that this H was coming from a collision resistant hash function family. So we conclude that this case, in fact, cannot happen except with negligible probability. And case two is H of M1 is actually not equal to H of M. And here A signed indeed a new message. And this contradicted the security of the underlying one-time signature scheme. right? So now the idea is we are just signing the hash. If the hash turns out to be different, then basically you are signing a different message. And if your original scheme was secure, this hash and sign would also be secure. If your hash turns out to be the same, then sure, you can use the same signature. But to come to this case, you have to find a collision in the hash function. And this is for one-time signature, but basically the same argument works, even if you're signing multiple messages. Okay, so this basically allows us to extend our previous scheme to still one time, but now we can sign arbitrarily long messages. Okay, any questions?
When you say multiple messages, you'll sign them only once, but you can sign more than one message.
No, this is still one time, but we can sign just arbitrarily long messages. We cannot sign multiple messages yet.
Okay, sorry, I think I misheard something. Thank you.
Yeah, I don't know, maybe I misspoke. Yeah, this is still a one-time signature scheme if you are starting with a one-time signature scheme. If you're starting with a multi-time signature scheme, then this gives you a multi-time signature scheme. But anyway, let's focus on one time for now. So now we'll go to signing multiple messages. And this is a very interesting technique. So I'll show you how to build a stateful signature scheme where, you know, key generation is the same as before. This is the definition, by the way. Define stateful signatures. Okay. The signing algorithm takes the secret key, the message, and some state. And then outputs sigma and new state. Let's call this new state, state prime. And next time when you sign, you want to operate on state prime. And verify algorithm is the same as before. We cannot really make verify algorithm stateless because, you know, there are many different verifiers. Verify algorithm must be public, so you just need the public key. And how does this help? Okay, the very high level idea is the limitation now is you can only sign one message with one pair of secret key and public key. Okay, but what if we could generate a new secret key and public key every time? That would be fine, right? That would be secure. But the problem with that is that now you need to keep changing your public key, which you don't want to do. In fact, the verify algorithm just takes a fixed public key. So that doesn't work. So the idea here is that you every time you do generate a new public key and secret key pair, and what you do is you sign the new public key with the old secret key. Okay, so public key I+1 is signed using secret key I. And then there's this whole chain. You need to verify the whole chain if you want to verify the signature. And let's see this idea in a little more detail. Okay, so now let's, we are given, let me call this G1, S1, and V1. which is a one-time signature scheme. We will define a new signature scheme, which will be a multi-time signature scheme. So what is gen? It's the run G1, output the public key which it produces, output the secret key which it produces, and by the way, initially state equals empty bot. How do you sign? You need SK, you need the message, and you need the empty state in the beginning. Okay. Now the signing algorithm runs G1 again, and you get PKI and SKI. Let's say this is the ith message which you are signing. Okay, so now what do you output? So now your signature sigma, let's call this sigma I, is equal to the following. So you use S1 on SK I minus 1 and the message that you want to sign concatenated with the public key PKI. And then concatenation mi minus 1 concatenation sigma I minus 1 all the way up to m1 and sigma 1. So your signature consists of the entire history of the messages and the signatures which you have produced, and the new signature which signs the new message and the new public key. And by the way, you need to add PKI, SKI, sigma I, and m equals mi to the state. And the verification algorithm takes the public key, the message, and the signature. Okay. And then verify the whole chain to recover PKI minus 1. And then verify sigma I on the message mi, which is equal to the message m. So the verify algorithm only has the initial public key, but fortunately it has all the messages, right? So it starts with the very first message. It verifies the first message, which also gives you the second public key. Then you go on, you verify the second signature, which gives you the third public key, and so on. And finally, you get the last public key, which is used to sign the last message. So that's the high level idea. If you want to encrypt your message, you should sign the ciphertext. Yeah, you can do that. You can encrypt and sign.
Professor, I have a question here.
Uh-huh.
So MI is basically M concatenated with PKI, is it?
MI is M concatenated with PKI. Yeah. And that's where we are using the fact that you can actually sign long messages.
Okay. Okay.
With a shorter public key. So the major limitation, of course, of this this scheme is that the signature keeps growing, the length of the signature. Right? The idea here is that every time you need to use a fresh secret key and public key, and hence you need to include the entire history, the entire chain. Okay, so what about improving the signature length? Is there any way we can improve the signature length here? What about using a tree as opposed to a chain? Okay, good. Yeah, somebody already suggested a tree out of the messages. Okay, and the way you would build a tree here is, instead of this, you would select 2 new public keys each time. So you would sign M concatenation, PKI concatenation, PKI prime. Okay, and the idea is that I don't need to give you the whole tree. I only need to give you the path from the root to the leaf. And let me not go into like full formal details of this construction. I think there are more details in the notes. But the basic idea is that each message belongs to one of the leaves of the tree, and you just need the public keys along this path. And once you have the tree, it actually dramatically improves the length of the signature. Instead of growing linearly, now you only have logarithmic growth, which is, exponentially smaller than linear. So any questions? So there are better ways of designing digital signature schemes. The nice thing about this was we only ended up using like collision resistant hash functions and just one-way functions. We didn't really use sort of any specific assumptions like discrete log or factoring, because the advantage of not relying on a specific number theory assumption is that even if that assumption is broken in the future, maybe another assumption comes in which will give you one-way functions, and then your scheme will continue to work, right? Any candidate construction of one-way functions and collision resistant hash function, it could be from factoring, it could be from discrete log, that's fine for the previous construction. But in practice, we want something even more efficient, and we can do that using RSA. So RSA signatures are very widely used. There's something which is known as ECDSA signatures, which are widely used, and so on. So we will look at RSA signatures. So interestingly, Rss Signature is identical to Rsa encryption, except that you switch the role of the public key and the secret key. And I should warn you that switching the role of PK and SK doesn't always work, right? For example, you cannot take Algamal and switch the role of SK and PK and hope to convert it into a signature. For RSA, because the process is just so symmetric, because in RSA, remember that encryption was sort of one exponentiation, decryption was also just another exponentiation. And these two exponentiations sort of cancel out. So this very nice property, this symmetric property of RSA is what helps us convert it into a signature scheme, or what helps us view it as a signature scheme. So let's see here. And by the way, Rss signatures or textbook Rss signatures, they are not secured directly, as we will talk about, and it's almost also the case with RSA encryption. I mean, RSA function really gives you a trapdoor permutation first, and then you need it to convert it to an encryption scheme. Similarly, in Rss signatures, first we will get something which resembles a signature scheme, but not quite. It will be insecure, and then we will show how to fix the problem. So how does the key generation work? As before, we will generate 2 primes, each of length n. Okay, we will sample E and D from Z of phi and star. And by the way, here n equals PQ, such that E times D must be 1 mod phi n. And then your public key is now E comma n, right? And what is your secret key? Secret key is D. How do you sign a message? The message must be part of ZN star, just like the RSA encryption. And to sign a message, you just encrypt it, except that you use D instead of E. So your sigma is m to the power D mod n. And as I said, the scheme is actually insecure, and I'll ask you why it is insecure. So verify PK, comma, and let's put n as part of the secret key also. So you need to test the following. You need to test if m is actually equal to sigma raised to the power E mod n. Okay. And when you compute sigma raised to the power E, E and D will cancel out and you will get m. And if this test passes, you output 1, which is accept, otherwise you output reject. Okay, so now, yeah. Now I am hoping somebody can tell me why this is a bad signature scheme.
So if like you have two messages m1 raised to the power of D and m2 raised to the power of D, then you can calculate m1, m2 raised to the power of D, right, by multiplying them?
Yeah, good. So this is by the way, this is called the homomorphism in RSA. RSA is a homomorphic signature scheme. It's a homomorphic encryption scheme, which leads to like all kind of interesting computations which you can do, which makes it insecure. So let's say you are given sigma 1, which is m1 to the power d mod n, and you are given a signature on another message m2. Okay. Now sigma 3 can be computed as, you just multiply these two signatures, and this will become m1 times m2 to the power d mod 3. And this is a valid signature on the message m3, which is equal to m1 times m2. Okay. So clearly RSA is not a good signature scheme. Now my next question is, RSA at least a one-time signature scheme? Which means that the adversary is now only given a signature on a single message. Can you compute a signature on a different message?
You can compute it on the identity, right?
Yeah, good. Yeah, there's also an answer in the chat. I mean, here we didn't use the fact that M1 and M2 are different, right? So it works even if M1 equals M2, right? And then your M3 will be M1 square, which is still not the same message, right? Might be different. So now the question is, how do we fix this problem? And this is why we say that textbook RSA is completely insecure. We should never even think about using it. And as I said before, this is known as the homomorphic property of RSA. Okay, so how do we fix this problem? Let's look at this equation. Let's hash the message before you sign it, and let's see what happens in that case. So now you just change the signature scheme, just change the signing algorithm so that as part of the public key, we also put a hash function. What type of hash function? One-way function, collision resistant hash function. I'll talk about that later on. Okay, so now the signing algorithm becomes sigma is hash of m to the power d mod n. Okay. Now let's say you want to forge, and again, how do you test? This should be equal to hash of m. Let me just edit the description here. Okay. How do you verify? You just test the hash of the message should be equal to sigma to the power e mod n. Now, does the forgery still work? So again, let's try to compute sigma 3, which now will end up becoming hash of M1 times hash of M2 to the power D mod n. And this is a valid signature on M3 if hash of M3 is equal to hash of M1 times hash of M2. Okay, so now we need a hash function where satisfying this equation is kind of hard, right? Adversary can keep trying many different M1, M2, and M3, and the probability that this equation will be satisfied is kind of small. Okay, now what if a hash function is a true random function? What is a true random function? It's a huge exponential size table. You can query with M1, you get some random string. Query with M2, you will get some other uniform random string and so on. So what if this hash function was a true random function?
So it won't be deterministic, right?
No, a true random function is deterministic. It's there's no, I mean, if you generate the whole exponential size table, all the queries can be answered deterministically.
Okay.
If you make the same query twice, you are going to get the same answer. So yeah, if the hash function is a true random function, then in fact, this works, right? The probability for every M1, M2, and M3, probability that hash of M3 is going to be equal to hash of M1 times hash of M2 will be exponentially small. It will be negligible in the size of the output of the hash function, right? Because these are just 3 random numbers. This is R3, this is R1, and this is R2, or I should say 3 random group elements. Here we are thinking about a hash function which gives you an output in Z and star so that you can apply the RSA function on it, right? So if these are 3 independent random group elements, the probability that R3 will be exactly equal to R1 times R2, that's going to be very small, negligible. Okay, but the problem, of course, is that we cannot really use a true random function. Storing that true random function will require you exponential time. Okay, so what if the hash function is a pseudo-random function? And we have seen before that pseudo-random functions sort of look indistinguishable from true random functions. So what if H is a PRF? And I'll tell you it doesn't work, but I'm hoping somebody can tell me why. One guess is messages are not uniform. That's fine. Messages serve as the index.
So isn't the property of true randomness of a PRF dependent on choosing the seed randomly? Like Here, who will choose to see it?
Yeah, that's a good point. And the point is, if I'm talking about a PRF, I really need to generate a random seed or a random key, and then I can feed it any message. And then the guarantee is that if key is uniform to you, let's say you are the adversary, then f of k comma some message is also uniform to you, right? But now the problem is we want our verification process to be public. Okay, if the verifier cannot evaluate the hash function or the PRF, then the verifier cannot verify the digital signature, right? So this means that K must be public. Now, if K is public, K is not uniform anymore. And then basically every security property of PRF, which we were relying on, that sort of goes out of the window. Okay. Nonetheless, in practice, this is called the random oracle assumption. Or it's also called the random oracle model. The model says that something like, let's say, SHA-256 actually behaves like a true random function. The code of SHA-256 kind of obfuscated, doesn't really make sense to you. You can evaluate it. You will find no patterns in the output. Even if there is no secret key, everything is public, you can evaluate it publicly. But basically, correlating the output is very hard. All the outputs on different inputs, they sort of look uniform, independent of each other, and so on. So this is a very strong assumption, but making this assumption allows you to do a lot of things, including get a secure version of the Rss signature scheme. Okay, so basically in the random oracle model, or assuming random oracles, hashing the message first basically gives you a secure signature scheme. And we will not try to prove it formally, but basically you can see that these kind of correlation attacks are very hard. So random oracle is really a very strong assumption. It means that the hash function is a one-way function, collision resistant hash function, behaves like a PRF with a public key, and a lot of other different things.
Why does a single collision resistant hash function does not work?
I mean, how can you prove that this equation is hard to satisfy for collision resistant hash functions? Collision resistance does not imply that this cannot be done.
It is difficult to find an M with H of M3 equal, so H of M1 into H of M2 is some value, right? So it is very difficult to find an M such that H of M equal to what? Like H of M1 into H of M2, like that. Why doesn't that work?
But where's the collision here? It's entirely possible that all three outputs are different, and yet the third output is the multiplication of the first two.
Right.
Right. For obtaining a collision, you need two outputs which must be identical. Here you are not getting that. All three are different. Okay, so I guess we will stop here, and I'm still around for questions for some time.